name is Sreyes Venkatesh of the UCSC Neuromorphic Computing Group under my professor, Jason Ishraghi. And today I want to talk about stateful quantization-aware training in recurrent spiking neural networks, aka SQUAT. So I don't think I'll need to tell this group that the development of low-power neural networks is crucial for enabling operations on edge and portable devices. To that end, one approach is dynamical sparsity, which is used by SNNs and their activations. In that when an SNN will receive a series of input spikes, if it's not sufficiently excited, it doesn't do anything. But if it is sufficiently excited, it emits an output. And then this is what's going on under the hood, where the neuron behaves as a first-order low-pass filter. And then our particular point of interest is when that membrane potential at the very bottom there touches the dashed line, which is what we define as our threshold, and that is where an output spike is emitted. Another approach for memory-constrained deep learning is to use fixed precision values, that is, go from 32-bit full-point precision values to lower bit representations of these values. There are also other methods such as pruning and distillation, but we choose not to focus on this for the extent of this paper. One thing that I would like to mention is that when SNNs are deployed onto their hardware, because the hardware and accelerators are inherently low bit or resource constrained, the SNNs are deployed in a fixed precision, using fixed precision values anyways, or inadvertently. Another piece of theory is that the compute complexity with respect to the weights is O of n squared, where n is the number of neurons, whereas with respect to the hidden states, it's O of n. However, this does not account for two things. One thing being that for our spiking neural networks, the binarized activations are usually like 1 to 5 to even 10% sparse, which means that not all the weights are being used. And also, unlike the weights, which are not really updated during the forward pass, the hidden states are updated every time step, which brings the computational complexity to be much closer to each other. And then this also gives us our motivation, because if we can improve the efficiency of the states, then it would be very beneficial for the overall network. And before I go more into the SQUAT, I would like to talk about the fixed precision approaches to current neural networks. The first one is post-training quantization, which is where we train the model in full precision, and then we quantize the weights at runtime during the testing phase. There are pros and cons to this. One pro is that because no additional considerations have to be made when training the hardware, when training on the hardware, this type of training is much easier and kind of cheaper and faster to do for the user. A downside is that because the training does not account for any of the error that would occur when the values are being changed from full precision to fixed precision, there is a large potential for worse performance in terms of accuracy and loss. The next method that we have seeks to alleviate the previous issue, which is quantization-aware training. For quantization-aware training, we start with our full precision weights. We quantize the weights during the forward pass. Then we calculate our loss with respect to these fixed precision values. And then we update our full precision weights with respect to this fixed precision loss. And then we go forward. This alleviates the previous issue with post-training quantization, where that the information that any error that would occur when there is a transformation from a full precision to a fixed precision will be more accounted for. However, since more information has to be stored, that is, the fixed precision values, the full precision values, and there are gradient approximations that need to be made, the quantization-aware training is computationally more expensive than a post-training quantization. And one thing that we would like to address is that historically, all the literature kind of quantization-aware training has been applied to weights specifically, not states. And also, as I said previously, when these SNNs are deployed onto the resource-constrained hardware, the hardware that is used to represent the bits is always going to be low, not full precision, which basically means that post-training quantization is being inadvertently applied to the states as we deploy them on the hardware, even though when the model is being trained, it's not accounting for that, which is what our method, squat, seeks to alleviate. So when we are quantizing our neuron states, obviously we want to quantize them as easily and intuitively as possible, but also as we go from low bit precision, such as like 8 bits, to even lower bit representation, such as 4 bits and 2 bits, what are the extra considerations that we can make to our quantization schema to account for this lack of resources but still maintain accuracy? So the first method is uniform squat. For a uniform squat, we set the minimum and maximal possible membrane potential levels, and then we quantize our intervals equally between those two, as kind of seen in this diagram. It is basically identical to how vanilla quat of weights is done. And as you can kind of see in this diagram, the full precision version is on the left. And because it's uniform squat, the differential, the DUQ over DU are all of equal sizes. And that's also represented in the steps of the quantized membrane potential. That when you can see all the heights of the steps are also equal size. Now, this is also some beautiful math that goes on how we can go from full precision to quantization, or to the quantized levels. But for the sake of brevity, I won't get into it. So uniform quantization is great, but one piece of intuition that we have is that the part that determines the network dynamics and activity is all behavior that takes place around the threshold. So it stands to reason that we would allocate more resources when quantizing around that specific threshold, since it is that threshold that determines whether the neuron is spiking or not. And to that point, we made or created exponential squat, which is similarly to uniform squat. We set the maximum and minimum membrane potentials, and then, but the quantization gets finer as it approaches the threshold. This is kind of reflected once again. If you look in the diagram, we have the full precision. We have the full precision membrane potential to the left. See, I don't know, start screen. We have the full precision membrane potential to the left. And then as you can see, the DUQ over DU is getting smaller as it approaches the threshold. And that again is also being reflected in the size of the steps, as the height of the steps is also getting small or gets smaller as they approach the threshold. And so now this is kind of the theory. And for the experimental setup that we run on it, we do a backpropagation through time with a surrogate gradient of arctangent for 100 epochs. It's 2024 also with the data sets. You know, there are bigger data sets than Fashion Eminence, Spike and Katelberg, and DBS gesture data set. However, and this is something I'll get into a little bit later, when we quantize our weights, we are quantizing every single state for every single time step. So the quantization process itself can become very expensive. So that's why we decided to use it with these smaller data sets to see and get like a diverse example. Or diverse returns. This is the experimental matrix. So first we run the quantization of just the weights, then quantization of just the states, and then quantization of the weights and the states. Then this is done for 2 bits, 4 bits, 8 bits. Then the same series of experiments is run for the same experiment is also run for post-training quantization. And then for the states I said before, we have uniform and exponential quantization. So then we double our number of tests to add to account for that. And then this right here is how you read it. So when we say quantization of just weights, that means we're using fixed precision values for the weights and full precision values for the states. If we say quantization of weights and states, then it's fixed precision values for weights and states. It's quantization of just the states, and it's fixed precision for just the states, put full precision for the weights. And then as we go through like the results, first I'll explain this graph. This is the performance of our model. On the y-axis, we have the accuracies. On the x-axis, we have the different quantization schema we're running, and that red dashed line is the full precision baseline, or precision value baseline. So first thing we saw is that the 8-bit quantization for fashionableness is very robust to all forms of schemata, basically saying if you have the 8-bit quantization, it did very well, no matter whichever way we tried to quantize it. We see that the specific benefits for squat appear at the 4-bit stage, and then also at the 2-bit stage. We also want to say that exponential quantization boosts the performance of squat even further, in that we can see that if we look at the 2-bit squat on the squat versus PTQ of exponential, and then compare that to 2-bit squat of squat versus PTQ uniform, the exponential performs much better than the uniform. And this is great news for us because it tells us that if you conscientiously, or the way you quantize your states makes a significant difference on your performance. Similarly, for spiking Heidelberg dataset, we saw similar trends as we did with fashion MNIST, in that the 8-bit quantizations are very robust, and that the exponential levels will always outperform the uniform levels for both PTQ and squat. And finally, we saw that for the PTQ, especially the 4-bit PTQ, for the uniform method or for the uniform quantization, it performs okay. But once you use the exponential quantization, the performance shoots up almost to baseline level of accuracy, which is very exciting for us. Originally, when squat was implemented, the vision for it was to be specifically for quantization-aware training, but now we're seeing that the exponential distribution of the states is also effective during post-training quantization, which was something that was exciting for us. And then since we saw that exponential was working better than uniform, we go into that a little bit more. For the exponential form, we can see that for 8-bit performs very well regardless of what the quantization schema is, kind of telling us maybe there's just enough information. We can see at 4 bits, the quantization-aware version does well, but the PTQ starts to degrade in performance. And then finally, we can see that at 2 bits, the SNN is more tolerant to a quantization of just weights than it is to a quantization of just states. This is very interesting because, as we said before, there are n-squared weights. So we would think that any change in the weights would be reflected in a greater change in the network than if we were to change just the states, simply because we can have more weights that we're working with. But this wasn't the case, and that's very exciting news. Then these are what we did for DVS. For DVS, for any form of post-training quantization, the network was very unhappy. Even for 2-bit uniform quantization of squat, the network was also very unhappy. One thing we found exciting was that for the 2-bit exponential squat, the network performed much better. And this was once again very exciting because we see that it is not only that is the way that you're quantizing the states of your networks that makes a big difference. And to see it make such a big difference was a very interesting finding. Finally, one maybe particular reason that for why the states make such a big difference is that we use convolutional neural networks. And for convolutional networks, the weight to neuron ratio is much lower or closer together than it would be for a standard network. So maybe that reflects in a change in the states making a much more significant change in the overall network. And then kind of summarizing all these findings. So overall, we see that the 8-bit quantization performs very robustly, no matter the schemata. And that is except for post-training quantization with devious gesture, which does not like any form. When we go down to your 4 bits and your 2-bit weights, that we would recommend where the quantization schemata matter. And then that's also where we maybe recommend putting in squat. One thing is I said earlier that the computational cost of running squat and quantizing networks can be very expensive, especially with something like 8 bits. So maybe do like a bit of a cost analysis benefit to see if if you maybe would need to run squat on that particular network, etc. Another thing we found was that enhancing uniform quantization with clipping is definitely something that we should look at, in that the maximum or the user can set the maximum and minimum membrane potentials when choosing to quantize their network. There are default values for this. However, we found that during the training and testing process, there were large outliers of, say, membrane potentials reaching, say, -100, -1,000 that were largely kind of disrupting our network. So by kind of clipping those values to, say, the minimum possible value would be 0, and then the maximum possible value would be around the threshold or slightly above the threshold, then we found that that greatly boosted performance. Finally, is something else, or not finally, but another thing that I've been talking about is earlier about how it's the state quantization determines the performance at lower bit widths, in that we just saw that there were so many more. We would think that because there are so many more weights, a change in weights would significantly alter the performance of the network, which is also in line with the current literature that we have of how weights are so important to performance. But we're seeing that the states are actually just as important, which was once again a very exciting finding. Finally, state-space models have a recurrent aspect to them. Spike neural networks also have a recurrent aspect to them. It would be cool to see if there was any overlap in kind of any of the work that can be done or something of that sort. And this was a demo. Click on the demo, we'll see. It's okay. Oh no, what's that? Okay, it's okay because I got pictures. So this is the code on how one would kind of implement the quantized network. So this is just me importing SNN torch and then importing PyTorch. And then after that, I'm importing the quant function. Then that first line of code, I'm defining what the parameters for my quantization scheme are. So I'm choosing to have 4 bits and representation 4 bits, and it's going to be a uniform squat. If I wanted to change it from uniform to exponential squat, I would just change uniform equals true to uniform equals false. Then after that, I am defining a single layer network with 10 LIF neurons. And you can see how that for me to quantize those networks, I just have to input the parameters state quant equals qlif, where qlif was a set of my parameters earlier. And that's all you should have to do. And now your network should be fully quantized. So ideally very intuitive, minimal code is possible. And then after that, I'm running just a forward random input and a forward pass to just get work. But yeah, so that's all I got. Thank you very much for listening.